Hi, this is Dr. Viv. I would like to solve a problem with three different interpretations of what the given quantity means. So you're given a mass density lambda, which is A times x, where A is a constant. Now, the units of mass density are going to be in kilograms per meter. X is in meters, therefore A must be in units of kg per meter squared. Now, the most straightforward interpretation of this mass density lambda is that it's a uniform thin rod of length L, and you're asked to find the moment of inertia about an axis of rotation that passes through the left end. Something like that. The second interpretation is that it's a uniform two-dimensional lamina of length L and width W, and you're asked to find the moment of inertia about the axis of symmetry, something like this. That's the length L, and that's the width W. The third interpretation that we're going to look at is that it's a uniform solid of revolution of length L and maximum radius R. So imagine that this is rotated about the x-axis, so you get a object that looks like something that you can turn in a lathe, wood sculpture or something that a woodworker would turn in a lathe, and that sculpture has got length L and radius R. The problem here is to find the moment of inertia under all these three circumstances. So let's solve this problem one by one. It's a really fun problem because it exposes the basic setup for the moment of inertia in all three situations. The easiest and the most boring, in a sense, is the moment of inertia for a uniform, for one dimension, non-uniform rod. Let's do this. We always start with a figure. So you have a rod that goes from 0 to L. The basic point element, the point element I'm going to indicate here, that's your dm. And for the one-dimensional case, it's always a point mass. The width of the point mass is dx. And the length is x. Now, the moment of inertia of a point mass is found simply by multiplying the mass by the distance squared. The distance is x, so it's x squared dm. Now, once we have that, we can find the moment of inertia by integrating. When I integrate from 0 to L, I get the full moment of inertia. Now let's put what my dm is. Dm is lambda squared dx. Lambda of x dx is what I meant to say. And lambda of x is given to us to be ax, so that's going to be ax cubed dx. So the moment of inertia about the axis, which I'll call, this axis I'll call y prime, it's just going to be the integral from 0 to L of the di. And so a can be taken outside since it's a constant. The integral of x cubed dx is x to the 4 over 4. Which gives me al to the 4 over 4. Now separately, I would also like to find the mass of the object, because I don't want to express it in terms of quantities like A, and L to the 4 somehow looks odd. So let's find the mass. The mass is given by simply integrating dm itself from 0 to L. The integral of dm is the integral of lambda of x dx. Well, it's given to be ax in our case, so it's integral from 0 to L ax dx, and if you carry out the integration, that's just ax squared over 2 from 0 to L, and that's al squared over 2. Observe that the units do make sense because the units of A are kg per meter squared, so kg per meter squared times meter squared is kg, so that looks like a good answer. Now what we're going to do is we're going to isolate al squared over 2 from the answer here. Well, that's easily done. Al squared over 2 times L squared over 2 is Al to the 4 over 4. So this answer can be written as Al squared over 2 times L squared over 2. So I'm going to get 1/2 ml squared. When you get a result like this for a non-uniform rod, always make sure that it passes the common sense test. The standard result for the moment of inertia of a rod about one end is 1/3 ml squared for a uniform rod. Now a uniform rod has got the same mass throughout, mass per unit length throughout, so you can expect a non-uniform rod with lambda given by A times x to have more mass as the rod goes further out, so it should be harder to rotate, and indeed 1/2 is bigger than 1/3, so this passes the test, for common sense test. Now for the more interesting problems. So that was the easiest of the lot. What if we interpret the object as a two-dimensional object of a laminar shape, which means flat? So let's draw the I don't yet know what kind of object this is, so I'll draw it as a symmetric but curvy shape. This is the function y of x that we seek to determine. The width is w, so this is going to be half width, w over 2. The mass element is now going to be a thin rod. So your dm is going to be a rod about the center. The advantage with using DMs with well-known results is that it makes our life simple. Now in principle this is a two-dimensional integral, but we don't ever want to do that, so we'll break things up so that we only have to do one-dimension integrals. Then you have the usual variables. X is the distance of the rod, we'll call the height y, and the thickness dx. The first thing we need to do is we determine the laminar shape. Let's determine y of x, and that's the laminar shape. So the idea is to look at mass density in a different way. Now mass density dm for this rod is also given by sigma naught, which is the constant mass density of this lamina. Sigma naught has got units of kg per meter squared, so it is an area density. Sigma naught times the area dA of the shaded part is the mass dm of the rod. The area of the rod is just the height, which is going to be it's y times this is y, and that's going to be another y, so it's going to be 2y times dx. And that must equal our other way of looking at dm, which is lambda of x dx. And so that's going to equal ax dx. If I equate these two things, then I can immediately solve for the value of y. So I cancel out the dx from both sides. I'm going to get sigma naught times 2y equals a times x. So this immediately gives me sigma naught. Well, I need to get the equation for y, so let me do that first. So this tells me y equals a upon 2 sigma naught times x. Well, that's just a straight line. It is still a good idea to determine sigma naught, so we'll do that next. To determine sigma naught, all I have to do is realize that when the value of x is equal to L, the value of y is equal to W over 2. So when x equals L, y must equal W over 2. Let's use that condition. So I get W over 2 equals A over 2 sigma naught times L. The 2's cancel out, and I immediately get sigma naught equals W. Sigma naught would equal AL over W. So that's great. Now I can find the equation y here. So y equals A over 2 times sigma naught, which is AL over W. 2 a's will cancel out, times x. So that's W over 2L times x. So that's the equation of the straight line. Beautiful. Once we have the equation of the straight line, the rest is going to be fairly simple. I'll substitute for the moment of inertia next. Actually, I would like to redraw the, it doesn't look good now that I know what it is. It's a straight line. So I'm going to redraw this figure. Because we know it's a straight line, and hence the lamina is a triangular lamina, I think a second drawing is justified. That width is W. And now I'll draw the element also. The element is this rod element of height 2y. X is the length, and dx, x is the distance of the element from the y-axis, and dx is the width. What we now need to do is find the moment of inertia about the symmetry axis. The symmetry axis in this case is the x-axis. Now the moment of inertia of the element is just that of a rod. The standard result for the moment of inertia of a rod, it's 1/12 ml squared. So in this case mass is dm, and L for a rod is the total length of the rod, which in this case is 2y squared. So this is a standard result for the rod about center. Now the 2 squared is 4, so 4 over 12 is 1/3 dm times y squared. But I already have my y and I have my dm, so I can substitute for that. Dm is lambda dx and lambda is ax, so that's ax dx. Y is found here, so I square that. I get w squared over 4l squared x squared. So all that is going to be 1/3 aw squared over 4l squared. There's x squared and there's a x, so that's x cubed dx. The integral moment of inertia I is just the integral from 0 to L of di. So I can take all these things outside since they're constants. So I get 1/3 a omega w squared over 4l squared, and then I just have the integral from 0 to L x cubed dx, which is x to the 4 over 4. X to the 4 divided by 4 between the limits of 0 and L. Let's substitute that in. So I'm getting 1/3 a w squared over 4l squared, L to the 4 over 4. One of the L squared factors cancels out. And now what I'm going to do is identify my mass. Mass is AL squared over 2. So if I take AL squared over 2, I'm left with 3 times 4 times 2, which is 24. So the moment of inertia is just 1 over 24 mw squared. That's a standard result, actually. You can look it up. It's the moment of inertia of a triangle about its symmetric axis, isosceles triangle. Isosceles triangle laminar. It's a standard result. It happens to be 1/2 the moment of inertia of a square or a rectangle laminar. Lastly, let us figure out the 3D interpretation, uniform solid of revolution. That's going to be the most interesting of all. Somebody in a lathe is turning out an object, and we have to help him decide what's the shape of the object. Let me draw the solid of revolution. I already know what it's going to look like. So to save time, I'm just going to draw the actual object here. And if you guessed it was a paraboloid, then kudos to you. We will determine it soon enough. The mass element this time is a disk. So you can think of this as a nose cone of a rocket or something, and if you chop it up, you have little disks that you can find. So that's going to be your y, that's x, the distance from the y-axis, the total radius is r, and your dm, the disk element, it's the disk about the center. That's also a standard result from the moment of inertia point of view, so we're all set here. So the first step, we're going to mimic all the steps for the laminar case. Let's determine the y of x after getting for the solid of revolution. This time, last time we equated the dm from the 2D perspective with the dm of the 1D perspective. This time we're going to do the 3D perspective. So we have, for the 3D case, dm is, so this thing is determined by a volume density rho naught whose units are kg per meter cubed. So uniform, if it's aluminum, it's going to be something like 2.7 grams per cc. That's what rho naught is going to be. So your dm is rho naught times dv. Well, the volume of a disk is just the area of a disk, which is pi y squared, and the thickness is dx. That's your thickness dx. But also we have dm equals lambda of x dx, and lambda of x in our case is ax dx. So setting them equal, we're going to get rho naught times pi y squared equals ax. And now we can solve for y. I'm going to get y equals the square root of some constant, which is a over rho naught pi, times x. The graph of y equals root x is a parabola. And if you rotate it, you get a paraboloid. Okay, so this object is a paraboloid. That's the technical name in multivariable calculus. So what we have to do now is determine rho naught. Well, that's easily done. Determining rho naught is merely a question of setting that when x equals L, y must be equal to R. So I'm going to get R equals the square root of AL over rho naught pi. Let's square both sides. So I'm going to get R squared equals AL over rho naught pi. And this immediately determines for me rho naught. It's just AL over pi R squared. I want to check the units. I always like to check units because it tells me if something's going wrong. The units of rho naught are going to be the units of A times the units of length over the units of R squared. So that's A is we've already determined to be kg per meter squared, and then length is just meters, and that's meter squared. So that's going to be kg per meter cubed. Standard interpretation of volume density. Let's also rewrite the shape of the curve. Y equals square root of A over, it's that one there, rho naught pi times x, and now we have got our rho naught. So why not get rid of it once and for all? Rho naught is not a variable in the problem. It's something I simply made up to set the problem up, so I have to get rid of it. Rho naught is all of that. Okay. And then there's also a pi, and then there's an x. So the pi's cancel out, A cancels out, and then I have R that comes out of the square root x over L. So that's looking really nice. The moment of inertia di is just 1/2 the mass times the radius squared. That's your standard disk moment of inertia, standard result, half mr squared. So the mass dm is lambda x dx, which is ax dx, and y squared because of that is r squared times x, no squared, x over L. So now I get ar squared over 2L x squared dx. Let us integrate. Integrating will give me the total moment of inertia I. All of these things in the front are constant, so I'll take them all outside, and then I get integral x squared dx, which is x cubed over 2 x cubed over 3, excuse me, 0 to L, and that's ar cubed over 2L, L cubed over 3, That gives me L squared. Now remember, AL squared over 2 is the mass. So that leaves me with 1/3 mr squared. I don't know if that's a standard result for the moment of inertia of a paraboloid, because it's usually not listed in the tables, but there you have it.